All right, well, we can start. So this will not be like a lecture, like a continuation of lectures. It's going to be like more like an advertisement of the of what you can do with this holographic duality that I'm lecturing about. So I will be talking about the applications of this holographic duality that comes from string theory in systems, in strongly interacting systems like that include heavy ion collisions or solid state applications. All right. So as you all know, or you have learned in this set of lectures, that most of the interesting and unsolved problems in physics today has to do with strong interactions, obviously, because if there were no strong interactions, we would be able to solve the quantum field theories that are describing these systems just by perturbative expansions. So, but there is if the coupling constant is large, the perturbative expansion breaks down, and we cannot really do perturbative computations, and this is a very important problem, of course. And this is not only a technical problem, it has a lot of applications. It's very important to understand our nature, like UCD, for example, the theory of strong interactions at low energies becomes very strongly coupled because the coupling constant in general in quantum field theory depends on the energy scale, and the running of the coupling constant in UCD is such that it becomes very large at low energies, where very important phenomena like confinement, degeneration of mass, etc. takes place. And so it's very important to understand QCD at low energies. And other examples in general in physics, like high TC superconductors, like fermions at unitarity, etc. So there are all these. I will not be really talking about fermions at unitarity, but there are it's enough to know that there are a lot of systems that involve strong correlations, not only in high energy physics, but also in condensed matter. And so if we can find a handle, some technical handle on understanding or approaching these problems in a completely different way, it would be very useful. So this is what I will be talking about. And this new technique essentially comes from string theory. There is one such technique, and it's called the holographic duality. So I will first talk about that a little bit. But this is all I said. But before that, just let me mention that you can, this is all about solving quantum field theory at strong coupling. Okay? So you can, the problem here is that the perturbative expansion breaks down. But in general, you can define quantum field theory on the lattice. You can just discretize your space-time, your space. You can put the quantum field theory on the lattice like this, with some lattice spacing A. Okay, by keeping this lattice spacing finite, you can define a quantum field theory there, and there you can do a lot of computations. It's a completely non-perturbative definition, so it doesn't really depend too much on the perturbative expansion. You can do computations there, but the problem with the lattice is the following: that there are again technical problems that are very old technical problems, like 30 years old technical problems. For example, if you have fermions with some finite chemical potential, like that you always encounter in the solid state physics, this approach, the lattice approach, doesn't work, because the lattice approach necessarily depends on the fact that you have a Euclidean. You define your lattice on the Euclidean space, on not space-time but just space, so that you can do some statistical computations like Monte Carlo simulations, etc. So you need to interpret that quantum field theory that you define on the lattice, the partition function, in statistical mechanics, as a probability distribution. Okay, so as a sum over different probabilities. So this is the Monte Carlo simulation. So, but you cannot do Monte Carlo simulations when you have fermions with finite chemical potential, because you get some imaginary factors, not real factors. Similarly, if you want to compute technically called Feynman diagrams, for example, or like Feynman two-point functions or retarded or advanced two-point functions that are real-time observables, not Euclidean observables. Again, you cannot do these computations on the lattice. And these computations are very important. For example, there are quantities, there are observables, like in QCD, there are observables called transport coefficients that are very important in the Hegelian collisions. For those quantities, or for computing conductivity in superconductors, you cannot do these computations. These quantities are, these quantities, these observables are all computed by calculating real-time correlation functions, okay, 2-point functions, for example. So you cannot do those calculations on the lattice. So what I will try to convince you is that, or just advertise, is that holographic duality helps with this problem. Okay? So, I mean, this will be, of course, just an overview. I mean, you don't have to, if you cannot follow all the steps, I'm not going to derive anything here. So if you cannot follow all the steps, don't worry about it. And if you want to know more about it, I'm lecturing tomorrow. So this is just some general words. Okay, so this talk will be general. So this holographic duality is a duality. A duality in general means that well, there are two. You can represent a physical situation, a physical system, in completely two different ways, completely two different representations, and it is just like a change of variables. But this is a very complicated change of variables. So in one case, you represent the same system by some quantum field theory in d dimensions, and on the other hand, you can represent the same physics by some gravitational general relativity, some gravitational physics in one dimension higher, d plus 1 dimensions. Okay? So the statement of holography, the word holography comes from the fact that if you have a space like a curved space with some boundary, like a ball, then the statement is the fact that this quantum field theory living on the boundary of the ball is the same, is dual to the physics inside in the bulk. Okay, so this is the idea. So I will just have a picture now. So this is the idea. Suppose that you have a curved space like this. So suppose that this is 4-dimensional. I cannot draw 4 dimensions here, but so imagine that this is 4-dimensional physics boundary, and this is 5-dimensional object in general. So that this is some kind of curved space. There is a radial direction, like the radial direction of the sphere, and this is imagine that this is the boundary of that sphere. And on the boundary, there is some quantum field theory defined, and you want to study the quantum field theory living here, which I take as a quantum field theory in Minkowski space. And then the claim is that the physics here can be described by the physics inside. But these two physics, I mean, this mapping is very different than the usual change of variables that you use in, for example, in quantum field theory or statistical mechanics. It relates completely two different observables. It relates the observables of gravitational physics with the observables of quantum field theory. Okay, so I don't know if you heard, but in quantum field theory, in the quantum field theory courses here, in quantum field theory, there is you have to define an energy scale, and all the observables depend on the energy scale. Right? So correlation functions like coupling constant, etc. They all depend on the energy scale. And this radial direction here is, in some sense, it geometrizes the renormalization group energy scale. So imagine that there is an object living here, which has some size. Since this is a curved space, as you move this object inside, it will become smaller and smaller. Okay, so this is just the change of scale of the object. So this is like geometrizing the idea of the idea that as you change the lattice spacing in quantum field theory, the objects change, they rescale. So the scale transformations are called the renormalization group transformations. And this idea of introducing the extra dimension, the radial dimension, is essentially just to realize this change of the quantities in quantum field theory as a function of the energy scale, to realize that in terms of geometry, just in terms of radial direction. Okay, so take the energy scale in your quantum field theory and replace it. Imagine that this is actually an extra dimension. So now you have 5 dimensions, 4 normal space-time dimensions, and 1 extra dimension coming from, which is the energy. So in this case, I'm representing that with the radial scale. And instead of having a 5-dimensional flat space, now you have to have it turns out that you have to have a curved space, 5-dimensional curved space. And this curved space is called anti-de Sitter space. So I will tell you what that is. Okay, so So the idea here is that this is the boundary of the curved space. As you approach the boundary, you are approaching to higher and higher energy. So this is UV. So being close to the boundary is like UV. But if you move the screen inside, you are probing the lower and lower energies of the quantum field. Okay, so this is the basic idea behind holography. Okay, so now again, this thing, I'm not deriving anything here, so I'm not going to be able to derive this fact. It's very non-trivial, but so believe this statement that if your quantum field theory, when the coupling constant in quantum field theory, normally we have a coupling constant where we make perturbative expansions, and we have some number of degrees of freedom. Like, for example, if you have a lattice gauge theory, a gauge theory with the SUN gauge group, with standard model we have SU3 times SU2 times SU1 times U1. But imagine that I want to study a quantum field theory with this gauge group, okay? And in the limit where this number of colors n is very large, and it's going to infinity. So now you can say that, well, this is not a very interesting situation because this doesn't describe real life. But actually, it turns out that large n is not that bad than n equals 3. So I will show some pictures, some lattice simulations that calculate the thermodynamic observables for SUN gauge theory and for SU3 gauge theory, and they will be close enough to each other. So this is not a very bad approximation, actually. Okay, so suppose that I do this approximation. I take this number of colors to infinity, and I imagine that I am in a situation in the regime of coupling constants where the coupling constant is very large, so G is very large. In this case, it turns out that the stringy physics, this comes from string theory, as I just remind you, that the stringy physics decouple, so you are only left with some classical gravity. So in this region, in this regime of the parameters, the claim then is that this quantum field theory living on the boundary of a curved space-time is the same thing as gravitational physics, just classical gravity. It's not in quantum here, just classical gravity in the bulk. Okay? All right. So then, of course, you can compute quantum observables like quantum correlation functions, like endpoint functions, etc., just by solving ordinary differential equations that describe how the particles, like classical particles, move inside the bulk. And one nice thing is that, as I said, lattice is bad. Lattice techniques are not very useful for like real-time correlation functions, like Feynman two-point function, etc., or when you have fermions around with finite chemical potential. But this idea works equally well with, in those situations. Okay. So then, of course, the main question that you have to ask, even if you accept that, okay, so this comes from string theory, very nice. But then the main question is, suppose that you give me a quantum field theory, and I want to find the curved background to be able to do general relativity, and then to relate the observables to quantum field theory. So the main question is, what is the GR background to a given quantum field theory? And this is the hardest problem, of course. All right. So, well, just to mention a few words about how this comes from string theory. It arises in string theory from objects called D-branes. So these D-branes are like membranes, but like higher dimensional, some generalized membranes. You can think of a membrane as, suppose that this is a T-dimensional. Okay? This is T plus one dimension, one time direction, T, and T space dimensions. Okay? So this is, in string theory, there are objects like this. So in string theory, we have closed strings and we have open strings. And this object couples to both. So it has so open strings can end on them, and closed strings can also source closed strings. They can propagate away from the D-branes. And if you study the how to describe the physics of these D-branes in string theory, you arrive at the fact that you can describe this physics of the D-branes in two different ways. One is by using just the open string description, this description, okay? Which just you can show. I'm not going to show here, but you can show that this can be described in terms of a gauge theory, okay, D-dimensional gauge theory. So So let me say that this is d-dimensional. Okay? So this will be this open string description is a gauge theory living on these d-branes, and usually it's an SUN gauge theory if you have n d-branes on top of each other. Okay? So this is a gauge theory living on these d-branes, and there's an additional description using this closed string. It's coupling to the closed strings, and in that case, closed strings have is nature. These closed strings are usually, you can think of closed strings as a generalization of general relativity. So the lowest modes of a closed string is a graviton, so it contains gravity. So this description gives rise to a curved background around this d-brane. Okay. So there are two different representations. One is in terms of gauge theory, the other is in terms of a curved background around the d-brane. So d-brane is a massive object, it just curves the background around it. So you have two different descriptions, and at some limit, when you take the low energy limit, these two descriptions decouple from each other and they become equivalent. So of course, I mean, these are just statements. I will drive these things in the lectures, but here I'm just advertising, but for the theory people. But here is just just to mention where this comes from. Okay. Now the problem with this description. Okay, so now this is coming from string theory, but this really relies on the fact that you have some d-brane description. Okay. So now let me come back to the main question. The main question was, if you give me a quantum field theory, what is the dual gravitational background? So what I have to do is that you give me the quantum field theory, I have to find a d-brane description, okay, where, suppose that you give me an SUN gauge theory. So I write down this d-brane description that you can do in string theory, and then what you have to do is to find the curved background, okay, the gravitational background that this d-branes describe in the second approach. But usually it turns out that this curved background, in most of the cases, is so complicated that you cannot really you can approach real-world physics like QCD. I mean, we don't know the appropriate d-brane description for QCD. Okay, so this is the main question. What we can do, for example, is so this is what I described in my last lecture. What you can do is the study in certain cases you can find. For example, a maximum is a very supersymmetric, n equals 4 supersymmetric, 4-dimensional, or 3 plus 1-dimensional Young-Mills theory, gauge theory, okay? SUN gauge theory. This we can do. And there are some other examples, very interesting examples that you can study with this approach. Okay, so is everything clear, by the way? Is the idea clear? If you have any questions, just you can interrupt me anytime. So then people said, well, okay, so this is too complicated. I mean, we can, okay, so in certain cases like this maximally supersymmetric theory, in 4 dimensions we can do it. Like there are 4 different supercharges in this case. It's a very exotic theory. It is like a gauge theory. It's not something completely different. It's a gauge theory that we, well, with some additional extra fields like fermions and some scalar fields in the adjoint representation, etc. It's not such a bad theory, but it's not QCD. So then people say that, well, I mean, we don't know how to describe this d-brane description. So let's believe that holographic duality is actually true. Is more general than this d-brane description. Or suppose that there is some d-brane description, but it's just that we don't know what is d-brane description. Okay, but still, this shouldn't be an obstacle in front of us. So what we have to do, what we can do, is to use the general principles of holographic duality that we learned by studying these examples to study more realistic cases. Okay, so how do you do it? So the idea here is that suppose that you give me a quantum field theory. So I know the properties of this quantum field theory. A quantum field theory has well, it is defined on some certain dimensions, right? So in d dimensions. In our world, it's 3 plus 1 dimensions. Suppose that you give me a quantum field theory in 3 plus 1 dimensions. I know that there's an energy scale. By the general idea of holography, this energy scale should be represented by the radial direction. So what I have to do is I have to go to a 1 dimension higher, right? So I have to look for a 5-dimensional curved background. Okay, so this is fine. And then that there are some symmetries of the quantum field theory. Like, for example, in QCD, we know that there are, well, first of all, there's a gauge symmetry. The gauge symmetry is automatically counts in this approach. And then there's flavor symmetries. Like in QCD, for example, if you have SU3 times SU3 flavor symmetry. So this SU3 times SU3 flavor symmetry should be able to realize in the curved background, in this curved space that you want to find. Okay, we don't know what the space is, but we are restricting the, we are just trying to find this curved space by restricting its properties. So then the symmetries of this quantum field theory should be realized as isometries, as symmetries of the curved background. So this is another property that we require. Another is that, well, suppose that you have relevant and marginal operators, which are interesting operators, like in SU and gauge theory, for example, the energy momentum transfer, or the Coulomb condensate, like trace F square. So T mu nu and trace F square, etc. So these are marginal operators. These are important operators, marginal or relevant in general. So for all of these operators, by the rules of this holography, what you have to do is you have to introduce some bulk field. Okay? So let me go back to this picture. So here, suppose that I want to describe the physics of these operators, like energy momentum transfer, trace F square, etc. Suppose that I have to calculate the correlation function of trace X square with trace F square, the two-point function of this operator. So what I have to do is I have to find a bulk field that couples to this on the boundary. So this is the idea. Then I can study the classical wave equation that is of the bulk field that couples to this in the bulk, and then from that I can calculate the correlation function. There, I will come to that. Okay? So for all of these operators, you turn on some bulk field inside the bulk, and well, if you have some additional phenomena like dynamical phenomena, spontaneous symmetry breaking, like Higgs mechanism, etc., in the quantum field theory, then there are well-defined ways of representing these things geometrically in the bulk. Okay? So once you know the properties of the quantum field theory that you want to describe, you can really restrict the properties of the dual background. Okay, so and it turns out that in some certain cases, these restrictions are universal enough to restrict the corresponding background and get universal answers. Okay, so this was the hope. This universality is the hope. And well, actually in QCD, for example, this hope is well realized to some extent, especially at finite temperature. And then you can do well, more or less reliable computations, almost at the same level as the lattice computations, and sometimes better with this approach. Okay. So the last step, of course, is that once you restrict these, once you have your background with these given properties, you just declare that this gravitational setup secretly describes the strong coupling regime of the quantum field. Okay. So of course, this is a phenomenological approach. It's not a derivation. It's just motivated by these D-branes in string theory, and this approach can be proven. In certain cases, this is you know how to do it exactly, but in more realistic cases, this is just a phenomenological approach. And then what you have to do is, suppose this GR theory is a description of quantum field theory, and then you can just do a calculation to check if this is correct or not. Right. So as I said, the universal lessons are important things. So let me give some details. Okay. So, all right. So this is the same picture again. So this is the curved background in 5 dimensions. This is 4-dimensional boundary, and this is called the domain wall type of background. And it has certain. It has a given metric, a certain kind of metric. This metric is just metric in general relativity in differential geometry is a way to measure the distances in curved space-time. So usually we have the metric for the flat space in quantum field theory. Our metric is just eta mu nu, which is minus plus 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 in 4 dimensions. But this is just a constant. In curved space, what you have to do is to generalize this thing to curve metric, which is a function of the variables, the space-time variables. And in this case, it is only a function of radial variable. So if it is only a function of radial variable, if it is written like this, then it's called a domain mole metric. And in holography, usually we have these domain mole metrics, some boundary. Okay, so there are two important things. The metric should be a function of the radial variable, and then there should be a boundary. As I said, this is a metric of a geometry in one higher dimension. So if the boundary is 4-dimensional, it is in 5 dimensions. This extra dimension is the radial direction. Right? Okay, so then once you have this background, once you specify this background by using the properties of the quantum field theory, then there are well-defined ways to compute quantities, like endpoint functions. As I said, if you have an operator like this or that in HMN, then what you have to do is you have to turn on some bulk field. This operator is living in 4 dimensions here on the boundary. This operator is living in 5 dimensions. One extra dimension is just so this is not an operator. This is a field that is living in one extra dimension. And the idea, this is a little complicated, but I will explain to you now. The idea is that if you take this boundary field, okay, so this boundary field is living in 5 dimensions, so it goes to the boundary. At the boundary, it becomes just a function that only depends on d variables, of course, d space-time variables. Right? And suppose that this boundary field goes to a function like this, and the idea is to associate this function, the value of this bulk field on the boundary, with the source of the operator, of the corresponding operator. So this is just a generating function. Okay, so you have a generating function to calculate endpoint functions. If you want to calculate endpoint function like this in quantum field theory, you have to start with a generating function like this, and then you take derivatives with respect to the source. Right? So that brings down, like, if you take n derivatives, it brings down n of these operators. And then from this expectation value, you can calculate the endpoint function. So the idea of holography is to relate this generating function to the action, the gravitational action, Einstein's action, okay? in one extra dimension, in 5 dimensions. And so you have to calculate the on-shell value of the action in such a way, with this boundary condition. With the boundary condition that this bulk field goes to this the source as you approach the boundary. Okay, so this is one bulk field. There is an additional way to introduce, and this is what I will come to now. Because these classical wave equations in gravity are usually second-order differential equations. So you need two different boundary conditions. One is just this, and the other is following. So in most of the interesting cases, we have to deal with a finite temperature quantum field theory. So that includes, for example, the heavy-ion collisions. So in the heavy-ion collisions, you have I will come to that, but you have a finite temperature QCD. QCD at finite temperature because you have many particles around. All these fluctuations create some finite temperature. And so for finite temperature, what you have to do in the dual approach, in the gravity approach, is to look at a black hole, because what you want to do is to introduce some finite temperature on the boundary. So you need to introduce some thermal fluctuations on the boundary. And the way to do this is just to turn on some furnace inside the geometry. If you have a black hole, as you know, the black holes radiate, and this radiation, as you approach the boundary, creates some kind of thermal fluctuations. So the way to describe the finite temperature quantum field theory on the boundary is to look at black hole solutions rather than just this simple vacuum solution. So you have to look at black hole solutions, and then the second boundary condition should be such that at the horizon, this is the horizon of the black hole, the event horizon, that nothing can escape from here to here, except the radiation gets smaller. So this on this boundary, on the horizon, you have to impose an additional boundary condition for this plug for the bulk field. Okay, so in most of the cases, it should go to 0. And for retarded Green's function, as I said, regularity at the horizon is important. So let's not get into the details, but this is the general idea. So if you want to study some finite temperature quantum field theory, and if you want to calculate the correlation functions of this finite temperature quantum field theory, like a retarded Green's function, etc., then there are very well-defined ways of doing this. Okay. Okay. So I don't think that I will have enough time to talk about all kinds of applications. So what I was planning to do was to to describe the applications in heavy ion physics first, and then applications to superconductors or superfluids in the second part. But I think I will not have too much time to talk about this. So what I can do, let's see. Okay, so let me start with the first one. Then if I have time, I will come to the second application. So this is the applications in heavy ion collisions. So heavy ion collisions are the following. So these are very important experiments going on in the world now. One is AdS that is running in Brookhaven, that is running since 2000. And another one is in LHC that is run. Well, the first experiment was done just 2 months ago. And so AdS, the idea is to take two beams of gold atoms and then collide them. Okay? So these gold atoms are at a very high center of mass energy, which is about 200 GeV per nucleon. Okay? Then after you collide all of this, so the gold atoms have a lot of nucleons inside. Okay? And just like the lead atoms also have a lot of nucleons inside. So once they collide, they release all these particles and these nucleons inside them. So they become free, and they just make some kind of a soup, which is actually a relativistic fluid. And then what happens after that is that this creature that is obtained, this kind of state of matter that is obtained after the collision, starts expanding. Of course, it expands, and as it expands, the thermal fluctuations die off, so the temperature goes down, and at some certain temperature, it cools down. Okay, as it expands slowly. Well, I will define what slowly is. Not that slow. And then after some time, it hadronizes. So inside the soup, there are only nucleons. Okay, so these are deconfined. This is the deconfined phase of QCD. So inside there are only like quarks. But after that, I mean quarks and gluons. But after some certain temperature, in QCD we have a transition from this deconfined phase to the confined phase at a certain temperature. And this temperature is about like 170 MeV. So at this point, it hadronizes, which means that these quarks and gluons just go inside the particles that we really observe in the detectors, like protons or mesons, etc. Okay. Sorry? As you go in energy, it increases. Yes. So, there are very strong experimental indications that this object, which is called the quark-gluon plasma, the soup, is actually almost like an ideal relativistic fluid. I mean, clearly it is relativistic because we are dealing with a relativistic situation here. It's very high center of momentum and transverse momentum. But it is the important thing is that it's almost ideal. Okay, which means that it's almost collisionless. It behaves almost like an ideal fluid. So it's very hard to find examples of ideal fluids in nature, but this is one example. It's almost like an ideal. And as I said, this is very interesting. I mean, interesting to study, of course, but for many reasons. One reason is just that this is a new state of matter. Quark-gluon plasma is a new state of matter. And another reason is that this is almost like a simulation of the universe right after the Big Bang. I mean, the temperatures are so high that it's close to the temperature of the universe right after the Big Bang, like 1/1,000,000th of a second after the Big Bang. All right, so that's why we would like to understand the physics inside this ball. Well, okay, so as I said, it's not very easy to study the system by doing quantum field theory because it's strongly coupled. As you were asking, it's very strongly coupled. I mean, you can infer that it's very strongly coupled from the fact that it behaves almost like an ideal fluid, which means that there should be very strong correlations inside all these quantum fluctuations in this fluid. Right? So it's very strongly coupled. And another thing is that, we don't know how to study strongly coupled theories by perturbation. We can put this on the lattice, but the situation here is a dynamical situation. It's not like a statistical. You don't calculate a statistical distribution. So you have to calculate real-time correlation functions to understand the physics of this object here. And those real-time correlation functions, it's very hard to do it on the left. So we need an additional approach. So this additional approach is what I would call a minimal holographic dual. So first I want to describe it at 0 temperature, then I will come to finite temperature. But I already mentioned, so the 0 temperature case will be just this domain wall geometry, and the finite temperature case will be the black hole. So it's, as I already mentioned, and I already mentioned this, that the lattice data, lattice QCD data indicates that SUN gauge theory is almost close enough to SU3. It's good enough, especially for studying finite temperature objects. So this is the first simplification I will do. I will replace SU3 QCD with SUN, and then I will take this number of colors to be very large. So this is the first approximation I will make. And well, the indications from lattice is that this is like almost 10% deviation from in the hadron spectra, so it's not that bad. And thermodynamic observables are very close to each other. I will just show a picture in a couple of minutes. And then I will consider this pure SUN gauge theory at large M at strong coupling, because I know that there's strong coupling physics going on inside the quark-gluon plasma. And then I will relate it to classical Einstein's gravity. So I will follow this phenomenological approach that I explained. Right? So this tells me that I have to go to 5 dimensions, and I have to find a curved space-time in 5 dimensions. The only relevant operators are the stress F square and the mu. There are no other relevant operators, because this is not QCD. This is like pure SUN gauge theory. If you take n to be large, then the quarks become not dynamical. That you can show by this quantum field theory calculations. Quarks inside the loops can be neglected, so they become non-dynamical. So you can ignore the quarks. So you can replace the quark-gluon plasma with only a gluon plasma. Okay, so I will describe, at least I'm aiming at describing the physics of this gluon plasma. Right? You have a question?
Strong coupling depends on the number of flowers, number of colors, but essentially now that's going to others have really
the relation between
Einstein general relativity and coupling.
Okay, I didn't have that. I didn't explain that, but let me just mention. I mean, I cannot explain it here because it will take me a lot of time. But the idea is that if you have strong coupling, well, first, so the idea, you can show that if you take the number of colors to be very large, if this is the case in quantum field theory, so this is the quantum field theory side, and this is the GR side. Okay. So if you take this, corresponds to the fact that there are coupling constants of the strings that describe the interaction of strings among each other. So these strings are interact with each other. So if there are diagrams like this, for example, and this comes to the factor of GS, the string coupling constant. This fact corresponds to the fact that this is going to 0. Okay. So in this case, you can ignore the string interactions, which is very nice. And the other fact that the coupling constant of the quantum field theory, CFT, becoming very large. This corresponds to the fact that there are all these excitations on the string, right? So you can ignore the string interactions, string excitations. So a string is like it has excitations on it. So you can replace this string with only the point-like objects, like graviton. Okay? Graviton is the low energy mode of this string. There are infinitely many excitations of this string. But if you take this limit, it turns out in the dual description, this corresponds to the fact that you can ignore all the excitations. And you are left with only a graviton. And the physics of graviton is just general relativity. Okay, so I didn't have. Okay, thanks for the question. So that I hope I made it more clear. Okay, so this is the second point, and the third point is that there's a running coupling in QCD. In SUN gauge theory, also there's a running coupling, which means that the coupling constant is a function of the energy, and in holography you relate the coupling constant with a field the bulk field called the dilaton. Okay, so it's phi, and the coupling constant is related to the dilaton in this way. And so the fact that this coupling constant is a function of the energy means that this dilaton should be a function of the radial variable, because remember that the radial variable and the energy are related to each other in this way. And so the dilaton, I have to find a potential for this extra field, the dilaton, in such a way that it runs. It becomes a function of R, which means that I have to introduce a potential, otherwise it wouldn't run. Okay, so therefore, the minimal setup is something like this. So what I'm showing here is Einstein's action for general relativity. So this is called the Ricci scalar. Okay, I'm introducing GR in the lectures now. So I didn't come to this point yet, but I will tell it in tomorrow morning. So this is just like, you can think of it as the kinetic term for the graviton. Okay, so it also includes some interactions. It's like a kinetic term plus some interactions of graviton with itself. And then there's this standard kinetic term. Forget about this coefficient; it's not very important. The kinetic term for this dilaton field. It's just an additional field. And then there's a potential, as I said. You have the tournament potential. Okay. So once you have all of this, we can look for these domain ball type of solutions. Okay, this kind of matrix where the dilaton also becomes a function of phi, and you can fix the asymptotics of the dilaton by requiring certain features of the quantum field theory, like asymptotic freedom and linear confinement. As you know, at zero temperature in QCD, the quarks are confined. Okay, so they have a linear potential among each other. If you from each other, the potential grows linearly as a function of the distance between them. So you require this. You require that QCD, the coupling constant in QCD runs in such a way that it becomes free. Theory becomes free at very high temperatures. So this fixes the asymptotic behavior of this potential here, and once you have that, well, you arrive, you can just write this phenomenal school approach. Let me remind you. So what you do is you just write down the potential like this, with these following, with these features, with the required asymptotics. But this is one example. You can do many, but this is one example. And once you have that, then you can do all these equations. And by fixing these four parameters by comparing with the lattice, then you can do calculations, and let me show you one simple thing. At zero temperature, you can calculate, for example, the blue balls. Okay, so the spectrum of blue balls. So, I said there are no dynamical quarks, there are only gluons, and these gluons are confined at zero temperature to in some blue balls. So this is one operator. So this is a glue ball operator. So this is colorless object, but inside it there are all these gluon fields. So you can calculate the spectrum of these gluons, and it turns out that these calculations that you do in holography is good enough. If you fix two of the parameters, and all of the rest are lattice data. Here I'm showing the lattice data. Here the result of the model, the holographic model that you do, you obtain, and it's good enough. Okay. So now let's come to the. But this is not the interesting thing. I want to come to the interesting thing. The interesting thing is to go to the finite temperature. And as I said, what you have to do at finite temperature is not looking at the domain hole geometry, but to look at the black hole kind of geometry. So forget about all these functions, etc. Here it's not very important. The only word that you have to remember is that I have to look at, if I want to study finite temperature quantum field theory, I have to look at the black hole background. Black hole is such that it has a horizon. Horizon means that this dt square, the function in front of the dt square, vanishes at some point, or h, which is the location of the horizon. Okay, so let me show you this picture again. So this is RH. Okay, so there's and this is zero temperature. At finite temperature, you have to introduce some function f of r in front of the dt square, and then you have black hole geometry. And once you have the geometry, then you can do calculations. You can do thermodynamic calculations. Okay, so this is the result of a thermodynamic calculation. So if you have a finite temperature field theory, one obvious thing to calculate is the free energy. Once you have the free energy, then you can derive all the other thermodynamic quantities. Right, so the calculation of the free energy here in the gravitational dual is done by looking at this action, this gravitational action. Right. So what you do is you calculate this. on shell on the black hole solution. Okay, so once you do this, then you have free energy. The rules of holography is such that these two are related. So once you do this, then you can look at the free energy as a function of temperature, and you find the result like this. So what I'm showing you here, okay, so is two things. One thing is that this is just pressure. It's a function of, this is just how pressure changes as a function of T normalized by this confinement, deconfinement transition. This dimensionless temperatures. So here, this is a result of the lattice simulation. Okay, so this person, Panero, did this lattice simulation for different cases. So he took like SU5, SU3, SU4, 5, 6, 8, and then calculated the pressure, which is the same thing as the free energy density, okay, as a function of temperature. So then he realized, he shows here, that they're almost on top of each other. So it's very close. So as you change this number of colors, the thermodynamic relation, thermodynamic properties of the system doesn't change too much. So this is one thing that I was mentioning in the beginning of the talk. This approximation of taking n to be large is not that bad. So this is one thing. And the other thing is that this holographic model that I'm mentioning, that I'm using here, is, you see, it just runs in the middle of these curves, so it's almost on top of this. Of course, there is some fine tuning here, but not much. I mean, you're not fixing the entire function. You're fixing just two integration constants, and then the rest is just prediction. And it works quite well. So, well, you can do other things. So once you have free energy, you can calculate, for example, the energy momentum tensor. And then from that, you can calculate the trace of the energy momentum tensor that describes how far you are from conformality. At high temperatures, the system becomes a free gas of gluons. So in that case, you have a conformal theory where this object goes to zero, and well, around the phase transition, it becomes very large. So this is the lattice simulation again, showing data for different kind of number of colors, and this orange curve here is the result of the gravitational calculation. So it's not, you see, it's you fix a couple of things, parameters, by just general requirements of quantum field theory, and then in the end you get nice predictions. But that's not. So let me. So how much time do I have? When did I start? We started late, right? I don't remember.
In 15 minutes.
Usually break for lunch around 12:30, maybe 15, 20 minutes. Would that be sufficient?
15 would be definitely enough. I mean, I was.
Okay, 15 is perfect.
All right. So okay. So now let me mention this thing, this transfer thing. So I will explain by words. Okay.
There is another speech, by the way, before.
Yeah.
Minus 15 minutes ago.
But we started like half an hour late. So can we move the speech after lunch, or can we? I mean, I can finish like in 2 minutes also. That's okay. But
Finish something and we figure out.
let me see your hands. Okay. So who are the people who would like to continue for 15 minutes? Don't be afraid.
Yeah, but what, I mean, the other two lectures will also do them too, right? So how will we modify the program?
Let's finish this and we decide during the lunchtime.
Okay.
All right. So. Right. So you can look at quantities. You can calculate quantities like some different things. Okay. So what I described to you, for example, here was just this the at zero order. At zero order in terms quantum field theory, what you do is you just calculate the free energy, you just calculate the thermodynamic functions, and at first order, what you do is so once you have this stable object, some thermodynamic equilibrium. So this object is quark-gluon plasma.
QGP?
Huh?
QGP?
Quark-gluon plasma. Okay, so this ball, this orange ball after collision. So at zeroth order, you treat the system as a system at equilibrium at some temperature T. System at equilibrium. And then you look at the fluctuations of the system. You do some perturbations. So you shoot it with some electrons, say, and things like that. So once you shoot, of course, if you fluctuate this object, then it responds. And this response is described by some correlation function. So suppose that you fluctuate the Lagrangian of that system by in this way with some operator. So this is a fluctuation, it comes to some operator. And then the response of another operator, the expectation value of another operator, the one-point function, due to this fluctuation, is given by the Green's function, the two-point function that relate of this operator OA and OB. Okay, so this is called Kubo's linear response theorem. This is a very general theorem, and this is very easy to understand. It's just so what you have to calculate. If you want to look at the system at first order, you need to calculate this OA OB, this two-point function. So in our case, we are fluctuating the energy and momentum distribution in the system. So we have to calculate the two-point function of the energy momentum transfer with itself. And so from this energy momentum, so the energy momentum transfer in relativistic theories is can be expanded in some parameters. So this is called the dissipation of the system. This is related. These coefficients are related how the energy is dissipated in the system. And this dissipation can be described by two different kinds of fluctuations. So if you have a system like this, so you can introduce two different kinds of deformations. What you can do is you can do a shear deformation. You take two layers and just move them to each other. Like this is called the shear fluctuation. And then there's a bulk fluctuation. You just apply some pressure and try to squeeze the system, and then it responds. So these responses are described by the shear viscosity and the bulk viscosity. And those two quantities can be calculated from different components of the two-point function. And this two-point function calculation can be done in gravity, as I said. And what we find is that if you calculate the shear viscosity in the holographic theory, what we find is that if you normalize the entropy density, you get something extremely small, 0.008, which perfectly matches the experimental data, by the way. So this was the first reason to believe that this holographic approach may be telling us something real. So that was the first thing that was done a long time ago, in 2002. And then you can calculate other things like bulk viscosity, for example. And this is more interesting because this thing is just a constant. But this thing actually is a function of the temperature. The coefficient of the energy momentum transfer that describes how the system responds to the bulk deformations. It's a function of temperature. And this function of temperature at confinement and transition at 170 MeV, it looks like it's extremely small as well, but it runs, and this is the result of the result. And you can also match this with some hydrodynamic simulations. Okay. Is there any question on this?
I read that this shear viscosity is some sort of lower bound, but I don't really understand.
Yeah. Okay.
Where does that bound come from?
This bound really comes from the fact that so in these calculations you are ignoring stringy moments in most of the cases. So you can what you do is if you include stringy fluctuations, the stringy corrections due to gravity. I mean gravity. When I say gravity, it's really gravity modulo stringy corrections. So if you ignore all the stringy corrections, if you start with the Einstein-Hilbert action, then you get this result, and this is very universal. It's universal, and then the idea is that, well, this is, if you turn on the fluctuations, the string fluctuations, this bound changes. It can go up or down. But this universal result is only by ignoring these gravitational these stringy corrections. And it's just a proposal. There's no proof that this is a lower bound. Okay, it's a proposal. It's just that you observe, you look at nature, and you see that, well, this is the smallest number that I can get. And there is a quantum field theory system that gives this number, which is just this system dimension, this is prismatic, four-dimensional Young's theory. Yeah, so on top of that, if you include also this small n corrections, you also get some corrections. So I mean, this bound is not very rigid. It's not very rigid. You can go around. You can move this bound even lower by some tricky corrections. Okay, but there is a nice universal result. For example, you can see also by low energy theorems in QCD that I think Alto will be talking about that. So this you can show by some field theory calculations that this object's bulk viscosity increases monotonically as you approach confinement, deconfinement temperature, and so this you can also show in horography. So this is some universal result. Let me stick this, and let me just mention very briefly what kind of horographic applications you can have in condensed matter systems. Okay, so I will just mention this and I will stop. Alright, so, well, there are many interesting, strongly correlated condensed matter systems as well. So, like high thesis conductors, like trapped Hall atoms, like heavy fermion systems, etc. So, these are all realized in the lab. So, this is very interesting to calculate. And of course, the way to describe them is by quantum field theory. But quantum field theory doesn't have very much. It's field expansion doesn't have very much. If you have strong correlations. And these lattice techniques are not very satisfactory, as I mentioned, because these systems all include fermions with at finite chemical potential. Okay? So then, well, you can say it's reasonable to expect that there is a strongly coupled dynamics. Well, if you look at the strongly coupled dynamics of these condensed matter systems, then it secretly possesses some gravitational description. In certain cases, you can derive this, as I mentioned, that there was this D-brane picture here. In certain cases, you can derive really, like M2 brane theory, etc., that the corresponding condensed matter theory can also be derived by this D-brane approach. But in most of the cases, you cannot. But you can still take this phenomenological approach and calculate correlation functions. And one example is that. These people in 2008, what they did was they found an explicit realization of a superconductor. Okay? A superconductor is an object where you have a U1 gauge symmetry, but this U1 gauge symmetry gets broken spontaneously, right? So this is, if you have this is not enough to have a superconductor, but this is necessary to have a superconductor. So if you have this this picture that you all know, this Mexican head potential. So this, right, so this is potential as a function of a complex field phi. Then this complex field phi is invariant under this potential is invariant under rotations. If you are here, the U1 symmetry is not broken, this rotation symmetry. But the potential is in such a way that a small quantum fluctuation takes you down here, and then this is spontaneous symmetry breaking. So here the U1 symmetry, the rotation symmetry will be broken, because the physics here is not necessarily the same as the physics here, but here it is the same. So this is one necessary thing to describe superconductors in quantum field theory. Okay? So this fact, this spontaneous breaking of a U1 symmetry, U1 gauge symmetry, or U1 global symmetry in their cases, was realized by studying this horography. Okay? So then the transition from a normal phase to a superfluid, superconducting phase is actually described by a transition from two different solutions in this gravitational theory. Right? So this phase transition can be realized, and there are many open issues. So let me, as I said, like there are these stringy corrections, 1/n corrections, etc. So these can be very important. These are all ignored in this approach. But what you can do is you can find different kind of approaches to study this problem. And this is, okay, so right now I'm working on finding different kind of solutions to this problem.
Parallel collision asymptotic freedom the thing is that
Quartz and gluons?
Quartz and gluon interactions.
Yeah, well, in the sp2 case, they don't interact. Yes.
How to chain link together quartz gluon?
Well, they come together at low. I mean, at low energies, the interaction is quite low. So as the interaction, if you increase the temperature, if you take quartz and gluons, put them together, and if you increase the temperature, at very very high temperatures, as you said, the system becomes a sp2 free, so they don't talk to each other too much. So they are free. Only if you go to small and small temperatures, there's this transition from deconfined phase to confined phase, where they start with the grouping together inside the hadrons. So it depends on the energy scale. Also, it depends on the temperature. Yes. So the question was a dynamical question. How does this work? Any other questions? All right. So I will finish here. Okay. So the thing is that the interesting thing is that you can also describe these Heisenberg type models, etc., which are used as models to describe the superconducting phase transitions in holography. So the problem with these models is that they're in more than 2 dimensions. We don't know how to solve these systems. They become very strongly coupled, and in the cases when they are strongly coupled, we don't know how to solve these systems. But holography can help. So I think I'll stop here.
Let's have a short lunch break.